The content in this presentation is covered on pages 206 through 211 of your textbook, and it's meant to help you achieve learning objective number 36, which is to explain why winds aloft flow roughly parallel to the isobars, while surface winds travel at an angle across the isobars. Be sure to skim the pertinent pages here before watching the video and read the chapter carefully before attempting any of the online quizzes. In this section, we're going to address airflow aloft that occurs at least a mile or 1.5 kilometers above the Earth's surface, where the effects of friction are not significant enough to influence flow. And then we'll analyze the winds at the surface where friction significantly increases or influences the airflow. In the last video, you saw a map that looks like this one, but that one was for surface winds, and this one is for upper level winds. One way to tell that this is an upper level wind is that the isobar labels look about 5 times higher than we would expect them to be if this were a surface chart. So I see numbers in the 5,000s. Hopefully you are all saying to yourself something like, wait a minute, air pressure is supposed to be lower at higher altitudes. These numbers are much higher. You are extremely perceptive. On upper level charts like this one, the isolines represent not the pressure, but the elevation of the 500 millibar or whatever pressure level it is, pressure surface. So this is the 500 millibar pressure surface, and I noticed that down here in Southern California, it's much higher above the ground than it is up here over the Great Lakes. So remember we said that pressure decreases by about 50% for every 5.6 kilometer increase in altitude. Look at the labels on these isobars. They're bracketing the 5,600 meter or 5.6 kilometer altitude. Notice too that the highest numbers seem to be in the lower latitudes. That suggests that if we started out at sea level in San Diego and climbed up a 5,600 meter high ladder, we would still be 190 meters below the 500 millibar pressure level. At the top of our ladder, the barometer would have a value greater than 500 millibars. However, if we started in Puget Sound up in Edmonds and we went up the same ladder, our barometer would show us that the pressure was lower than 500 millibars. And we'd have to climb back down between 10 and 70 meters somewhere to find the 500 millibar surface. So at the top of the imaginary giant ladder, there are actually fewer molecules above our head in Edmonds than there were in San Diego. On the upper atmosphere chart, you can see that there is a big blue H near the southern tip of the Baja Peninsula and a big red L just to the south of Anchorage. The upper level pressure regime is illustrated in the cartoon below the map. So near Baja, you would have to climb 250 meters higher to find the 500 millibar level. Near Anchorage, you would have to climb down 470 meters to find it. So notice too that the isolines north of the high pressure centers on the map point to the north. This is called a ridge of high pressure because of how it appears in the cartoon below the map, like a ridge. The transparent gray shaded sheet in the cartoon is that 500 millibar pressure level. And it's higher than average along the ridges. South of the low pressure centers, you can see those isolines sort of making this big loop that dips to the south. On the cartoon below the map, that forms a trough of low pressure. Looking at the wind vectors on the map, you can see that winds aloft tend to flow parallel to the isobars. They don't cross. In regions where the isobars are relatively straight and evenly spaced, the resulting winds flow in a straight line and parallel to the isobars. That phenomenon is called a geostrophic wind. And it's generated when a balance is reached between the Coriolis force and the pressure gradient. This figure illustrates the formation of geostrophic winds, and you begin with a non-moving parcel of air directed by the pressure gradient force from an area of high pressure near the bottom to the low pressure area at the top. Initially, the parcel of air has no motion, and the Coriolis force is non-existent. Under the influence of the pressure gradient force, the parcel begins to accelerate from the area of high pressure to the area of low pressure. So as soon as the parcel begins to move, the Coriolis force commences and causes deflection to the right for winds in the northern hemisphere. As the parcel accelerates, the strength of the Coriolis force increases, and you can see the length of the vector labeled CF increases. Right? That Coriolis force is represented by a vector, which is an arrow. It's any quantity that has a direction and a strength or a magnitude. Remember that the magnitude of the Coriolis force is proportional to the wind speed. The greater the wind speed, the greater the deflection. So eventually the wind turns so that it's blowing parallel to the isobars, at which point the pressure gradient force is exactly balanced by the opposing Coriolis. As long as those forces are balanced, the wind continues to flow parallel to the isobars at a constant speed. Stated another way, the wind is coasting, right? It's not accelerated or decelerated along the path defined by the isobars. Under those conditions, when the Coriolis force is exactly equal in strength to the pressure gradient force, but acts in the opposite direction, that airflow is in a geostrophic balance. Geostrophic winds flow in relatively straight paths, parallel to the isobars, with velocities proportional to the pressure gradient force. A stronger pressure gradient, contour lines squeezing closer together, makes a stronger geostrophic wind, and a weak pressure gradient, with contour lines farther apart, is a lighter but still geostrophic wind. So it's important to note that the geostrophic wind is an idealized model that really only approximates the actual behavior of airflow aloft. Under normal conditions, isobars are rarely straight and seldom are they uniformly spaced. So the winds are never purely geostrophic. But nevertheless, that model, the geostrophic model, offers a very good estimate of the actual winds aloft. By measuring the pressure field, the orientation and the spacing of the isobars aloft, meteorologists can determine both wind direction and speed. Occasionally, isobars on air pressure maps connect to form roughly circular cells of either high or low pressure. So unlike geostrophic winds that flow along relatively straight paths, winds around bends and in cells of high or low pressure follow very curved paths. Winds of that nature, which blow at a constant speed parallel to the curved isobars, are gradient winds. That figure shows the gradient flow around a center of low pressure. So if there's a low in the middle, that's called cyclonic flow. As soon as the flow begins, the Coriolis force causes the air to be deflected. And in the northern hemisphere, where the Coriolis force deflects the flow to the right, the resulting wind blows counterclockwise around the low. Around a high pressure cell, the outward directed pressure gradient force is opposed by the inward directed Coriolis force. Right? You can see the blue is the result vector. If you look at this one up by the starting point, the red arrow shows us the pressure gradient force path, right? That's the direction that the air molecule wants to go. The black arrow shows you the Coriolis force, which pulls it to the right. And so the resultant wind is the big thick blue arrow, which is not going along that pure pressure gradient force, but somewhat to the right of that path of motion. So that is an inward directed Coriolis force. The clockwise flow is also known as anticyclonic. The figure on the right is all about the anticyclonic flow. Because the Coriolis force deflects the winds to the left in the southern hemisphere, the flow is reversed, right? In the southern hemisphere, we would see clockwise flow around the low pressure center and counterclockwise flow around high pressure centers. And I get nervous telling students about this sort of thing because there's so many binary options that matter. Sometimes it's best to make yourself a little table that outlines conditions in the northern hemisphere. So in the northern hemisphere, airflow in cyclonic systems goes counterclockwise. In the southern hemisphere, when we have cyclonic flow around a low pressure center, Coriolis works the other way. So we would see clockwise flow there. And of course, exactly the opposite conditions occur around high pressure centers. So, clockwise around low pressure centers, counterclockwise around high pressure centers. Meteorologists call centers of low pressure cyclones and the flow around them cyclonic. And there are several types and scales of cyclones. Large low pressure systems that are major weather makers in the United States are mid-latitude cyclones. Other examples include tropical cyclones, which are generally smaller than mid-latitude cyclones. Tornadoes, another example of a cyclone. Those are tiny and extremely intense cyclonic storms when you think about the grand scale of the planet. Cyclonic flow has the same direction of rotation as Earth, counterclockwise in the northern hemisphere, clockwise in the southern hemisphere. Centers of high pressure are called anticyclones and exhibit anticyclonic flow, opposite of the Earth's rotation. So remember that whenever isobars curve to make elongated regions of low and high pressure, those areas are called troughs and ridges, respectively. The flow around a trough, because there's low pressure in the middle, is cyclonic. Conversely, the flow around a ridge is anticyclonic. So consider the forces that produce the gradient flow associated with cyclonic and anticyclonic circulation. Wherever the flow is curved, a force has deflected the air or changed its direction, even when no change in speed results. That's a consequence of Newton's first law of motion that states a moving object continues to move in a straight line unless it's acted upon by an unbalanced force. So you have undoubtedly experienced the effect of Newton's law when the automobile you're riding in turns sharply and your body tried to continue moving straight ahead. The figure on the left shows us that in low pressure centers, inward directed pressure gradient is opposed by the outward directed Coriolis. But to keep the path curved or parallel to the isobars, the inward pull of the pressure gradient force has to be strong enough to balance the Coriolis force, as well as to turn the air inward. The inward turning of the air is called centripetal acceleration. Stated another way, the pressure gradient force must exceed the Coriolis force to overcome the air's tendency to continue moving in a straight line. The opposite situation exists in anticyclonic flows, where the inward directed Coriolis force must balance the pressure gradient force, as well as provide the inward acceleration needed to turn the air. So notice that in the pressure gradient force and the Coriolis force, they're not balanced. The arrow lengths are very different, as they are in geostrophic flow. That imbalance provides a change in direction that generates curved flow. If you imagine these being a cyclonic and an anticyclonic flow system side by side on the surface of the Earth, maybe this one is over Nevada and this is over Nebraska. Bayes-Ballott's law helps you figure out where the high pressure and the low pressure are located. So as you've seen, wind direction is directly linked to prevailing pressure pattern. So if you know the wind direction, you can also establish a rough approximation of where the pressure centers are. And it's a straightforward relationship that was invented or discovered in 1857 by a Dutch meteorologist named Bayes-Ballots. The law states that in the northern hemisphere, if you stand with your back to the wind, low pressure will be found to your left and high pressure to your right. So you can imagine yourself standing here with the wind at your back. See how it's moving in this direction here, and it's also moving in that direction there. So we would expect the wind to be coming from behind us, right? If we're looking in that direction. So over here to the right is the high pressure system. Over to the left is the low pressure system. Friction as a factor affecting wind is important only, like I said before, in the first mile or so of the atmosphere, 1.5 kilometers. We know that friction slows the movement of the air. By slowing the air movement, friction also reduces the Coriolis force, which is proportional to wind speed. Because the pressure gradient force is not affected by wind speed, it wins the tug of war against the Coriolis force, as you can sort of see happening in this diagram. The result is that the movement of air at an angle across the isobars toward the area of low pressure. The roughness of the surface determines the angle at which the air will flow across the isobars and influences the speed at which it moves. Over relatively smooth surfaces where friction is low, air moves at an angle of 10 to 20 degrees to the isobars, and its speed's roughly 2/3 of a geostrophic flow. Over rugged terrain, where friction is high, the angle can be as great as 45 degrees from the isobars, with wind speeds reduced by as much as 50%. We learned that above the friction layer in the northern hemisphere, winds blow counterclockwise around a cyclone and clockwise around an anticyclone, with winds nearly parallel to the isobars. Combined with the effect of friction, we find that surface airflow crosses the isobars at varying angles depending on the terrain, but always goes from higher to lower pressure. In a cyclone, in which pressure decreases inward, friction causes the net flow of the wind towards the center. In an anticyclone, the opposite's true. Pressure decreases outward and friction causes the net flow away from the center. So the resultant winds blow into and counterclockwise about a cyclone and outward and clockwise around an anticyclone. In the southern hemisphere, the Coriolis deflects the winds to the left and reverses the direction of flow. So regardless of the hemisphere, friction causes a net inflow, a convergence around a cyclone, and a net outflow or a divergence around an anticyclone. Use the course content provided on the Canvas site as well as outside internet sources to verify that you can formulate answers to these questions. If you can comfortably answer them, you're in great shape for the test. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.